Okay, thank you guys. Let's talk about this. So, predict the frequency of a photon. So straight away you know you're looking for f of a photon. And all you're told is that an electron, some electron has had a change in energy. The change in that electron's energy is 5.43 times 10 to the negative 19. Now, this idea of the electron having a change in energy is really important. You might remember quite a long time ago that we said we can actually not ever measure the absolute energy of anything. All we can measure is changes in energy. We don't really know what zero is, okay? So we can't say the electron has this much energy. All we can say is it takes this much energy for something to happen, okay? In this case, all we can say is it's lost this much energy. We can just measure a loss of energy. And the assumption that those of you who have gotten the correct answer have to make is that that lost energy from the electron is equivalent to the energy given to some photon that we created. Okay. So you would have rearranged that equation to give the frequency equals the energy divided by Planck's constant, which is just 5.43 times by 10 to the negative 19, divided by 6.626 times by 10 to the negative 34, which ends up giving you times 10 to the what? Positive? Yeah. Which is a pretty high frequency. Yeah, I'm not sure that those numbers are realistic, but that's fine. So that's the premise that we spoke about last time of the Bohr model, okay? This idea that we can actually lose an electron. An electron can lose energy in its orbital around an atom. And in losing that energy, it has to go somewhere. We're pretty comfortable, hopefully, by now with the idea of conservation of energy. So that energy must go somewhere, and it goes into the emission of a photon. And this happens all the time on the grand scheme of things, and we spoke about the issues with the Rutherford model, right? The problem with the Rutherford model was it predicted that the electrons would require centripetal acceleration. For electrons to centripetally accelerate, they actually have to radiate out energy. And we kind of did see this to some extent. We saw energy coming off all atoms. That's what blackbody radiation sort of proved us, and we could exactly predict that radiation. But it didn't match up with the idea that if those electrons were orbiting and they were losing energy that way, they should spiral into the nucleus, and then, you know, that wasn't what we observed. And also, they should be releasing some continuous value of energy, little tiny amounts bit by bit, okay? Not what we saw, which is the spectral lines. So the Bohr model addresses that by proposing that there's stationary states and they only decay to a ground state, and then they can't decay any further, okay? And that's what we now accept. Now, in, hello, tab, there we go. What they did, you guys saw those spectral lines. You can get them pretty accurate out of a hydrogen globe normally. And a lot of what we're going to do from now on, we're going to focus on the atom hydrogen because it's the most simple element and it's the first sort of prediction of this. And it's obviously been extended to other atoms, but you don't need to know the other atoms. So we're just going to talk about hydrogen for a little while. In 1885, so before even the Bohr model had come along, they found that there was a relationship between those spectral lines, okay? So, do I want to look at that yet? No. I don't have spectral lines. So, when you get those colored bands, you know, you might get a blue band here, an orange band here, or whatever. And that gives you some amount. What's blue? Towards ultraviolet. Smaller wavelength. 400? I should know this off the top of my head, but I don't yet, so there you go. 500 for blue? And orange? 700? 600? Whatever. whatever it was, right? What they found was that whatever these bands were, maybe there was a purple one there, which was 300 or whatever. What they found was there was some discrete multiple they could use to actually calculate this consistently every time for hydrogen, but not just for hydrogen. Hello, pen? Having technical difficulties today. Not just for hydrogen. They did it first for hydrogen, right? And they said, oh, hydrogen, I can calculate perfectly what wavelengths of light it can produce. And initially they might have only seen 3 bands, but then somebody did some experiments and they realized actually you can get a 4th band, you can get a 5th band, you can get much higher energies if you want. You just have to do special things to it. But they perfectly predicted all of those bands with this small little calculation, just like, double it or times 2 minus 3 or something like that, right? This simple relationship. We are actually going to look at it in a second. It's not that simple, but it was a nice sort of clean multiple, right? They also found it worked for a helium ion. Now, our chemists in the room will know helium normally has 2 protons, so therefore 2 electrons. When it's an atom, those 2 electrons fill that first shell. We can, of course, get helium ions, which only have 1 electron. It's not common in chemistry, it's very rare, but you can ionize helium so it only has 1 electron. Guys, focus up. When they heated up helium ions, they found the exact same spectral lines. Now, what does that tell you about those spectral lines? What does it relate to? What does hydrogen and a helium ion have in common? Same number of electrons. And so that electron would be ionized in the same way and move up in electron shells in the exact same way, okay? It would go from n equals 1 to n equals 2, and it was just the 1 electron, right? So a very predictable pattern of energy. And that's how we came up with Balmer's equation. Now, in your notes, I don't expect you to copy all of that down. This figure, I'm probably going to always just project for you. I might even get it printed so you can stick it in your books, actually. But I would encourage you to grab, I think you already have a Bohr diagram with your n equals 1, n equals 2, n equals 3 states in your last examples. If you have space near that, just chuck Rydberg's constant there and identify that the n states match those n states. So the energy level is always given by n. Make that very clear that that n is not just some arbitrary number, it is the number of the energy state, okay? If we can get some good notes on that into our books as best you can, and then we'll talk through it in a second. Again, I don't need you to copy that big box of the energy level diagram. Talk about it. Thanks, guys. So, hopefully, and I know I'm asking you guys to connect a lot of different ideas together here, all right? I'm assuming you're comfortable with conservation of energy. I'm assuming you're comfortable with the Bohr model of the atom. I'm assuming you're comfortable with what protons and electrons are. And I'm assuming you have your heads wrapped around the idea that photons come in discrete packets. If I'm assuming any of that unfairly at any point and I say something that doesn't check out or doesn't make sense to you with your current understandings, Campbell, please stop me and just ask the questions, all right? Let me know if there's something you're not sure of. This is tricky stuff, and it's just going to get harder, so make sure you stop me. So we have this Bohr model of the atom, and the Bohr model came along and cleaned up a lot of things about our confusion with how the atom was working. We already had the Rutherford model, which was pretty good, that planetary model. That checked out with a lot of experiments. But the Bohr model resolved the idea of emission spectra. So discrete packets of energy coming out of things when they were emitted, and resolved a lot of black body problems and things like that. Now, this is that nice, pretty little constant value that I told you we can use to predict the sort of energy coming out of this. Basically, just we need to wrap our heads around this energy level diagram. And it is actually kind of simple, all right? I want you to ignore all these blue lines for a moment. Ignore all of that. all right? I want you to focus on just these black lines and the energies next to them, okay? Just focus on them. And you can see this first line here is the ground state. Now again, the ground state is here. It's that first orbit. It's the electron cannot go any further towards the nucleus. And it's in terms of space here, and this sort of answers the question, possibly inadequately, of why the electron and the proton don't sort of stick together. This is them being as close as they can be without occupying the same space. Amusingly, they actually can measure from these calculations. Oh, I just used an eraser, sorry. From some of these pieces of math that we've established, including the orbital, the angular momentum, which has radius in it. From that, they were actually able to calculate the radius of the ground state, and it's something like times 10 to the negative 11 meters, which is not really that small of an amount when we're talking about an atom. So the distance between the nucleus and the first state, or the ground state of the electron, is actually quite large. But that's as close as they can be without occupying the same space in terms of physical things, right? Two balls can't just be in the same spot. It's the same thing with a nucleus and an electron. So that ground state we say is n equals 1. And we need to get comfortable with this idea of n referring to those energy levels. And we say it has an energy of negative 21.7 by 10 to the negative 19 joules. Now notice that that is called E1, the energy when n equals 1, okay? And that goes on and on, E2, E3, E4, E5, right? And this formula tells us how that changes. So the energy of some energy level n is just equal to E1 divided by n squared. So if it's 2, if you go from energy level 2, it's just 2 squared, 4. It's just a quarter of the energy of level 1. So about a quarter of that would be about negative 5. There we have it, negative 5. So it was a really simple, clean, I guess that's an inverse square relationship if you were to graph it. Now, we have to talk about this negative, all right? Why a negative? Does anyone have an intuition for why in the lowest state we say that the energy is negative? And maybe you want to think about, what are we talking about? The energy of what? Right, the energy of the electron. Now, if that's a negative value, what would be the energy 0? We talk about here, n equals 5. That's in the 5th energy level. We still have a little bit of energy. What would energy of 0 look like for an electron? Right, a free electron. Now, does that mean that electron has no energy? No, because what are we talking about here when we talk about the energy of an electron? A change, absolutely. We cannot, I shouldn't use the word absolutely. We cannot find the absolute energy of an electron, okay? So we're talking about the change in energy. And what we're saying here is when an electron falls to the ground state, it has lost energy. It has less energy. And that makes sense intuitively. If that then became a photon and was emitted, the energy that the electron has lost becomes the energy of the photon. Ask questions if that didn't make sense. Question? They must have an absolute energy, right? No, and I think possibly someone's come up with a scale for it, but similar to the Kelvin scale, right? We can never actually get anything to 0 degrees Kelvin, because that would imply that it has no energy. And to my knowledge, we've gotten quite close, but it's theoretically impossible to sort of actually get something to have 0 energy, because even just to observe it, you sort of energize it in a sense. So it's a similar idea. It's hard to ever see anything with no energy, and it's hard to know what that scale would look like. But I think there probably is a predicted scale for the amount of energy in various atoms and stuff. But yeah, very hard, not worth talking about for now. So how's that intuition, this idea that electrons sort of lose energy as they fall to the ground state? They're less energetic. Is that fine? And that's why we see the negatives in the energy. Okay, cool. So we can calculate the energy at any n state, and we can use this to do that, right? A change in energy is the energy of the final state minus the energy of the initial state. Now, in terms of negatives, you'll have a change in energy is some negative number minus some negative number. So you end up adding that next number, which gives you a slightly smaller number closer to 0, but still negative, which gets a little bit confusing. But again, that's the energy of the electron, change in energy of an electron. Okay, I would encourage you to add that somewhere and identify that that is change in energy of an electron. Now, of course, if we had some change in energy of an electron, what does that change in energy create or become? Radiation. Yeah, a photon, specifically a single photon with a discrete amount of energy. It can only have energy in intervals from these different energy levels. Okay, so it can never have a change of 3 by 10 to the negative 19 joules, right? Although that's pretty close, that's 3.02. But it's always a set amount. It can't be just any amount we think of. So when I gave you this question, that change in energy of that electron, we can then use that to predict the photon that would be emitted. How are we feeling? Are we connecting the ideas here? Or have I lost people? Now, you might notice some other changes with this energy level diagram, a couple of additions that I hid from you for this part. So the full energy level diagram includes the different series, and you'll notice n equals infinity, which has an energy of 0. What's n equals infinity? What electron has an energy state of infinity? A free electron, an ionized electron, right? Now, this is where things get a little bit gray area, because the reality is an electron could be across the universe and still sort of have some theoretical attraction, right? It approaches 0, the amount of electrostatic attraction, but it's never 0. So it gets a little bit gray there, but the idea is you could be at some infinite energy level, and there's possibly all these other energy levels in between. And if you're doing chemistry, I think they teach you up to n equals 7, or they talk about up to n equals 7. That's about where anything practical stops. We're not that bothered about all of the energy states. I think that's a field of ongoing research, so you can be involved in that if you want. But n equals 5 is sufficient for us to do some pretty cool calculations and predict the energies of some interesting photons. Now, these series are just, we've named after the people who sort of were responsible for their research. So the Balmer series, it's Balmer's equation for a reason, right? He was one of the first to predict this, and he worked on atoms falling from various states into the second state primarily. So he wasn't getting the research on the ground state. That had already actually been done by Lyman. He just didn't know what it meant at the time. And then other people who managed to get electrons to decay from n equals, let's say n equals 7 down to n equals 3, and see what energy change that was and what photons those produced, and bracket and fund. I don't need you to remember that sort of stuff, right? I do need you to appreciate that there is some infinite energy level where there would be no change in energy, right? If you fell from a free electron from an ionized state down to the ground state, what would be the change in that electron's energy? If you had some free ionized electron drifting along, it found a nice fluorine atom, and it was like, hey, I'll make this fluorine an ion. I'll give it that one extra electron. No, that's a bad example, actually. Hydrogen. Finds a hydrogen atom. Finds a hydrogen atom, and it falls from being an ionized electron down to the ground state. Becomes the ground state. Okay? Yeah, it would. 21.7 by 10 to the negative 19 joules would be the electron's change in energy. Is that energy that the electron has gained or lost? The electron loses that energy. So a free electron being absorbed by an atom and becoming the ground state electron would then emit a photon with how much energy? photon with 21.7 by 10 to the negative 19 joules. And that photon would have almost 4 times as much frequency as this, right? Energy frequency proportional, 4 times as much frequency. It'd have a frequency of about 32 by 10 to the 14 hertz, which is a very high energy photon. So more energy in the photon, the higher we drop. Questions? Have a think about it. Connect it to some other ideas. Think back to what we were doing here with those emission spectra. And then answer the question I gave you at the very start. How come when you point that thing at the sky, you see a whole band lit up? Doesn't that defy the idea of Planck's quantized energy? If you get a continuous light band across the wavelengths? What do you think? Lots of lights. So most of that light's being generated by the sun. Different elements. Sun primarily fuses hydrogen into helium, and it's only in the collapse of the sun that we often get heavier elements. But yeah, there's probably a lot of elements up there that are actually on fire in the sun. So what does that mean? Right, so if you have 3 bands from hydrogen, 3 bands from helium, 3 more bands from lithium, whatever their bands are, if you have bands for different atoms, for different elements, you can end up with what looks like a continuous spectrum. But again, it's actually still quantized. You cannot just pick a number out of a hat and say that that is the amount of energy there. It's just that the quantization of it is by 10 to the negative 34. Which is an incredibly fine resolution. So you probably could come up with a number, and it would happen to exist. But there are a series of numbers, a series of wavelengths that cannot exist. They're just very, very small, I guess is the best way to describe it. All right, let's do some questions. If you have questions, ask. I'm just going to grab your little check for understanding here. Yeah. There we go. Couple of steps to that. Hopefully it's made enough sense that you can connect it all together and follow it through. So 2 ways of solving it. There's the first way. Hands up if you solved it that way. How many people use Rydberg's? Cool. So obviously, for those of you who didn't do that, Rydberg's constant is given. It is in your formula and data book. Can someone tell me? I mean, they get the right answer from that. Yeah, you got 103 nanometers. Oh no, you'd get the inverse actually. So what do you actually get here? R times 89. No, that's after you inverse it. 111.975, and then 1111, and then 0.111111. Ah, weird. And that equals 1 over lambda, so you then need to actually divide 1 by that, and you get lambda equals 1 divided by that, which is 1.03 by 10 to the negative 7, or, remember that by 10 to the negative 7 meters? 103 nanometers. Because by 10 to the negative 9 is your nano, so you multiply by 10 squared, which gives you by 10 to the negative 9 on your units. Now, the other way of solving that was just using the change in energy, which is EF minus EI. And that ends up being negative 21.7 minus negative 2.41, all by 10 to the negative 19. Little trick there, remember, with your units. You can do the SI notation outside brackets. That gives you negative 19.29 by 10 to the negative 19 joules. Now that change in energy of an electron, the absolute of that is equal to the energy of a photon. Okay? Which is equal to HF, or HC on lambda. Therefore, lambda equals HC over absolute value of change in energy, the energy of the photon, which ends up being 103 nanometers as well. Questions? We've got 7 minutes left. Happy for us to sit and stare at this for a while, or chuck some more bulbs on or something, and just discuss. That's Balmer's.